But we're going to start with these four, okay? So the first one is conocer. Conocer means to know. But remember, conocer is to know people, places, or meeting someone for the first time. Is saber. That is to know facts or knowing how to do something. But conocer is to know people or places. Or when you meet somebody for the first time. So conocer is an irregular verb because of to go for. You cannot say conocer. All right, that doesn't sound right, that's well right. So we have to add speak in there. So it's conocer.
Hi, Miss Danny.
Good morning, how are you? Conocer. Then.
Miss Danny, I found 7 more brownie points.
Write them down, let me know what they are.
I have one brownie that got that they called me.
You what?
He's like a roll. I have one brownie that was freezing in my house.
It was freezing in mine this morning.
Like 30 or something.
I liked it though. I left something upstairs and we can write that.
Even better. So everybody wants to do moving. And the one is one of the. It's four.
I found 7 more brownie points. Probably next week we're gonna get brownies. Probably.
Where's Miss Danny? And then
She's probably in the bathroom or something. Smells like falling here.
No.
Oh, there. Louis and Darcy went to
Two people at once, go ahead. Go ahead. What were you saying?
by the way, Louis and Darcy went to vacation.
They're on vacation, yes, they said that last week. What were you saying? Oh, there's no one else right there. No problem. Sorry, Emma, were you saying something too? Was everybody talking to me at one time?
I was camping in North Carolina.
Oh, was it fun?
Yeah.
Paper towels on the counter?
I
or something?
couldn't comment on the video,
Okay.
but I did comment on the
The assignment in
Yeah.
the, okay, all right, I'll see it then when I go in. And if I miss it, let me know, so.
and also I answered my question. I was not in traffic. I was camping. So I thought that would count like as recognition that I did.
There you go. That's good. Excellent.
Also, do you like my outfit?
I like that.
Pokemon.
Yeah, you don't
I have
know. Thank you, sir.
Pokemon Club, so I am prepared.
I love it. Very, very good. Very, very good.
I've control.
Fix that.
Anything wrong with
And
I'm so confused. Did I read the wrong lab?
Well, no, you don't have, there's nothing
I
in
mean-
your binder for today, because you're gonna, it was all kind of a surprise, I didn't want you to look at it ahead of time. So you'll get it today. Once we all get in here and get situated, that's when you'll get it.
Okay, but I'm confused because there's a thing to read.
Thing to read in the assignment?
Yeah,
Yeah, the stuff about,
light.
light, no, light,
I must have read the wrong.
yeah, we'll figure it out. I'll think you can. We'll figure it out.
Yeah.
Maybe.
I got this shirt and this jacket at Walmart yesterday.
Oh, well, there you go. Always a win. When you find good stuff that you like and it's not a gazillion dollars, that's a win in my opinion.
Last one, and
Jack gave me that.
Oh, yeah.
Yeah, you're good. Yes. Jack gave me that. It came from Calvary. And Calvary, the last one, where you guys go. And I got that same year, I liked it so much, I got my mother, that was what I got for Christmas, it's a glass one. And those ornaments are hanging above the bar.
I don't think Jack made that one, but we did do glass blowing.
Yeah. Oh, we were going to get one, gee, that's it. It's, and not the.
And there's,
Yeah. That's cool.
You have to leave your baby. You always got to go home. So when you know that you can't say this, right? Oh. No, it doesn't work, right? No. So I'm gonna say Dale. Dale. And then it's Dale. I'm gonna give you this in regular.
Looking at all my weird things?
Miss Danny, did the tinker did come?
Not yet. You'll know. There's no way to miss it. I'll send text, whatever, anywhere else. It's obvious. Oh, that's a fun one, right?
I wish Tinker Day comes on a Tuesday.
I do too. It did.
Was
it last year?
Yeah.
Yeah, I was gonna say it did either last year or the year before, so.
I hope it doesn't because you can get 5 extra credits.
That's true. You can get a little more extra credit.
I have a question.
Hmm.
You said if I want face paint, you're wearing face paint. Does that count as wearing green and gold?
Oh, you mean like for a Halloween costume?
No,
What do you mean?
for
Like if you-
extra credit.
If you put some, sure.
If I put okay,
That's green and gold. That's wearing.
I thought so. I was just wanting to make sure.
That's
My
wearing.
sister has a face paint set.
Oh, yeah.
Okay,
So
second,
you can do green and
second
gold.
question.
Yes.
Does a goldish yellow count as gold?
Oh, absolutely. I have lots of goldish yellow. It's the closest you can get sometimes. So yeah, I've got that. I'm excited. Yesterday I was checking the weather in Roanoke. You can always check the weather in Roanoke. If it's gonna rain, you know it's not gonna be Tinker Day. So I was checking the weather and it was supposed to be nice today. It was like a high of 65 and good and cold this morning, which means they've had a frost.
Tinker Day ever happened on a Halloween, which happened on a Tuesday?
I don't know about the last part, but
Tuesday too,
I know, that's why I said y'all can wear costumes if you want. And,
but I'm not wearing costumes on.
ooh, careful, don't leave these. We've got a very fun lab that, do you see that pile is your pile right there? No, the pile of, yeah, those have your name on, 'em, right? Yes. They're just playing. Anyways, oh, let me take Darcy and Lewis's stuff back. So I just slapped it down like I always do. Even though they are on.
I spent like so much, like around like 15 minutes getting on.
Oh my gosh, you spent a lot of time. Morning, people. How goes it? Come on in. I put yeah, there's your homework right there. Alrighty. Love it. People are showing up. Where in the world I put my earbuds? It was the weirdest thing. They're supposed to be in my pocket, but it's weird.
Fun lab day.
It's a very fun lab day. It's kind of a,
But there's no written lab, right?
no, I'll give it to you today when it's time. Like it's supposed to kind of be a surprise, so I don't give the whole thing to you ahead of time because I don't want you trying any of the tricks ahead or
Oh, because-
looking it up because it's fun.
Easy to do.
Well, some of them aren't too difficult to like try at home, you know, and others are a little trickier, but none of them are very hard. Of course I won, he says. I like that. I like,
So
of
would I.
course I won. Duh.
I tried to make that and it backfired.
I like him. He's
Should've gone
cool.
with them.
Yes, I have a lot of favorites, so.
Oh, we didn't have. You know, I think I need a mechanical pencil again.
Oh, here, I think I should have one in here that's, oh,
I can't not use mechanical
I think that one has lead. No, I don't blame you. I don't, yeah.
I can't. I'm open.
It's much my preference, and I know when I was a kid, when I had the wooden ones, I would start chewing on them. Because I like the way it feels when your canines poke into the wood.
It does feel very satisfying.
It is, yeah, when you're bored in class, it's great, and I used to get bored a lot, because they would go over stuff a gazillion times, and I'm like, I got it that first time. Well, I think this is us for today, because the Armstrong kiddos are, where are they? Does anybody know where they are?
They went to the
The beach, which beach, do you know? Oh, like Hilton Head or something?
We
Very
just went to
nice.
North Carolina.
Where'd you go?
Asheville.
Asheville's beautiful, I have friends that live there.
It was like, it was,
Mhm.
where was it? But it had that outlook that was like.
Oh, like a big overlook.
like this.
Oh, did you go to, no, it's okay. Anyway, Asheville's lovely, I have some friends that live there.
North Carolina.
Where'd you go?
Near Cherokee.
Okay,
We went.
you
we
went
went to-
camping, yeah.
Yep, we ride the train, we went zip
Oh,
lining and we went rafting on the literally worst possible day because all
Been
day,
cold.
except the day we were rafting, were sunny.
That was
and
cold.
Semi-warm in the afternoon. It was.
Oh, my
very-
goodness, yeah, that's no fun. No fun. Okie dokie, so,
But Danny, I
Yes.
can tell, it says read chapter 10, section 4 and 5,
Mhm.
but that's, my book is like.
it's what? Light? Oh, it's light, oh, no. Huh. All right, let me look real quick and see, maybe you have a different edition. There are actually 2 editions, or 3 or 4 editions of this book, but 2 that are popular, and it might be that you have a different one, so.
It's Danny,
Yeah.
Back. You asked me to switch the books.
Did
That
I,
one my brother got and the lab rats one I got, and then like I checked in the chapter section and I found that out like in the lab rats.
oh, you mean when I put your names in them, I put them backwards? Oh, well, I'm glad you caught that.
And then me and my brother's books.
Yeah, Chapter 10, 4 and 5 should be action reaction. So what, your book looks like this? Okay, so you probably have, so what happens is there are certain school districts, big ones, not districts, but like a state, for example. And they'll say, well, we want the same textbook, but we want it ordered differently. So a good trick is if you, so you might have one of those. So if you look and it says light and you're like, that doesn't make sense. But you look here and it says action, reaction, and universal forces, then the good thing to do is to go up to your table of contents and see like, where is action, reaction, and universal forces in my book? And then you can read that one, because it's gonna be the same stuff. It just might be in a different order, and it happens sometimes, not a huge deal, but it's a bigger deal with the senior class. Because I request them to get the Florida edition specifically, because it has like 4 extra chapters. So if they don't have the Florida edition, then the one they have is missing like 4 whole chapters. So I actually had to scan them all and make a PDF of those for a couple people. Well, this is us. So we'll go ahead and start, because this is a fun class and this is going to be a super fun lab. And the next 2 labs are actually, after this one, are all fun. So all of this stuff is good stuff. All this forces business. All right, so there's my little Newtonian rat, right? My little Newton dude. I like his little velvet vest, his little pookie belly. All right, so
Is this a recap?
this is Newton's third law. So we did first and second, and this is lesson 9. So what?
Supposed to do the, what is it called? The test?
There's no test yet. You got test is after lesson 11. If it's like a homework, it'll say, well, you shouldn't be able to access the test yet. Because it's not open. The test isn't open yet. You talking about on teacher days?
Yeah,
It had a test?
the unit 3 test.
Shouldn't be accessible. I'll double check it. If you did anything with it, I'll try and clear it out. I might not be able to. I might have to do something different. Sometimes it won't let me clear out, but I'll figure it out. I'll look today when I do all my grading. So like I sent in an email like 2 weeks ago, I told you guys that my Tuesday afternoons have changed entirely. So basically, Drew's gymnastics team has had to shift from like right over here in Cumming to Marietta. And we have to carpool, and it's because it's a long way. So we have to carpool, and Tuesdays are the day that I don't want to do because I want to sit here and get my work done with grading and cleaning up and everything. But the other moms can't do Tuesday. I just don't want to do Tuesday. So I'm like, okay, I guess I have to. So now I have to leave here at like 3:30 or 3:15 every Tuesday. So it's only like an hour and a half or 2 hours after y'all have left. And then I have to drive all the way to Marietta, and I try to do my work there, but it's distracting because it's a gym full of people. So
Well, you have a very good reason not to do it.
yeah,
Want to do it.
yeah, I didn't want to, but this year it's not such a big deal. Next year it'll be a real big deal because chemistry, some of those chemistry labs take me like 2 hours to clean up. They're really involved, and I would let you all clean them up because it's good practice, but I don't want anybody to, this sounds terrible, break my glasses. Because if I break my lab glass, then it's on me. But if you break my lab glass, I'm like, oh, why'd I let him do it? So yeah. All right. So Newton's third law. All right. According to Newton's third law of motion, I need light on the screen. Whenever one object exerts a force on a second object, the second object exerts what, Emma? What?
Two things.
Yeah.
Your TV is not.
Oh, shoot, it just went
And
away.
this
Thank you for
man-
telling me. I
And
will
this
fix it.
mechanical pencil is not.
Oh, boy. Okay, hold on. I didn't know it just died on me. It was up there and then it disappeared. Let me see if I have another one somewhere. You got a mechanical pencil that doesn't like you. You may have to settle for a pencil. Let me see if I can make this one sharp for you. All right, just be sure to get that one back. It's a Baylor pencil. I don't have another one at the moment, at least not. I have to bring more down, I guess. All right, so let's try and fix this since it disappeared on me. Ugh. Why'd you do that? Don't do that. Oops. Okay. There we go. Fortunately, it only takes a second to pop back up. But I found that if there's not something active on the screen, sometimes it'll cut out. So like if I don't move fast enough, it'll cut out on me. All right, here we go. So here's our Newton guy. All right, okay. Go ahead for it, Carlos.
Equal enough.
An equal and opposite reaction first on the first object. So this is one of those that you've heard before. Now, did you see that? Watch that animation again. He kicks the ball, bonk. Yeah. So the ball made the wall kind of wiggle when it hit it, but knocked him over, right? Equal and opposite. So there are what and what forces. Do we know what we want here? Something and something. Emma? Motion. It's a good guess. What you got, Eunice? Equal and opposite forces. Okay, so we're going to go with action and reaction forces. Okay, so forces have equal and opposite reactions. So if you kicked the ball, that would be your action. And if it bounced back off the wall at you, that would be a reaction, right? So the easy way to remember Newton's third law is this line right here, right? Every action has an equal, I should say has, an equal and opposite reaction, right? All right, so Newton's third law tells us of these 4 characteristics of forces. So forces always occur in what? What you got, Nico? Thinking about it. Action and reaction. Do you know, Eunice?
Forces occur in
It's a tricky one. So pairs. So forces will always occur in pairs. You have an action and a reaction. Do you know what else works in pairs in your body that you may not even think about? Your muscles. Yeah, your muscles work in pairs. So you have one muscle that will allow this, and there's one opposite. One will contract and one will stretch out. There's pairs. So when one does one thing, the other does the opposite. That's how you're not like, you have a little control, right? So action and reaction are what in magnitude? They're equal and what? Oh, sorry, opposite and what? There you go. The opposite and equal. Okay, so they're equal in reaction. Action and reaction are equal in magnitude. If I dropped a ball and it bounced back up to my hand, I drop it from here, right? And it'll bounce back up. It won't quite reach my hand, will it? And then the next time it'll go lower and lower. How can that be if these action and reaction forces, this would be the action and the reaction would be coming back? How is that? Why doesn't it come back up every time if they're equal in magnitude? What do you think?
Because it's if it bounces, it's like the opposite.
That would be the opposite. So that's the reaction. But why doesn't it come all the way back up? What do you think?
It uses energy when it uses energy when it touches the floor.
It does. So there's a lot of laws of conservation in science, not conservation like keeping nature well, not using our resources, not that kind of conservation, but there's law of conservation of matter, of energy, of momentum. So in this case, if you're thinking about law of conservation of energy, so if I drop the ball, when I'm holding it here, it would have what we say is gravitational potential. Yeah, potential, but specifically gravitational potential energy. And if I let it go, that energy, when it hits the floor, some of that energy is going to get absorbed into the floor, like the wood around it some of it will get pushed through, and some of it would be friction. And if I dropped it again and again and again and again, eventually the spot, if you hit the same spot every time, would start to get warmer because friction releases energy as heat, right? Okay. So, did you have a question? Yeah.
No, I think because the ball comes out because gravity pulls it and keeps pulling the ball.
Yeah, and that's the other thing. So gravity's always pulling, right? So gravity's always pulling that ball down, and it has to have enough energy to keep escaping that pull every time. Another type of potential energy. So if you have a toy and you notice it no longer works, you usually, if it's a toy that like lights up or moves across the floor, you usually have to open it up, and what do you have to do? Put new batteries in it, right? Okay. So a battery on its own, it's not doing anything, right? You can sit it on the counter. It's not like making things happen.
It has potential.
It has potential. If I have a ball here and I'm holding it up and ready to drop it, if that's gravitational potential, what kind of potential do you think a battery has? What do you think?
Energetic potential?
It has a type of, it's a type of energy potential, but do we know what kind? Do you know what you think? What do you think?
Here is power.
It's actually chemical. So batteries have,
Oh yeah.
Yes, chemical potential energy. Yeah,
that way.
you don't think about it, but it absolutely does. And it's actually the gravitational potential energy, and then the kinetic energy, which is motion, which we're going to be talking about all that soon.
That's
Right.
Kinetic potential. Wait, no.
Kinetic energy is energy in motion.
Right.
And then potential is like everything waiting. Yeah. So those forces are what like shape our whole planet. Like our gravitational potential energy, and then our gravitational kinetic when it starts moving. That's what makes rivers flow closer and closer. They're always going down, right? Trying to get to the center of the earth. They're never going to get there, but they try. And that's what causes, valleys and all kinds of things to form. That's all the same type of energy. All right. So action and reaction so first we said they're equal in magnitude, and they're what in direction, Eunice?
Opposite.
They're opposite in direction. Okay. Opposite in reaction, and they act on different bodies. Okay, so that's important to remember, because sometimes you have a force like multiple forces happening to one body, but they can act on different bodies. Then we call them action reaction. All right, so what are some examples of that? All right, so here we go. Not all action reaction forces produce motion. So in this case, we have Beatrix. All right. The weight of Beatrix is acting downward on what? What do you think it's acting on? What's her weight acting on?
The table.
The table, okay, it's acting on the table in a downward direction. All right, so why does it say weight and not mass? Why do you think I said the weight of Beatrix and not the mass of Beatrix?
Mass is like.
He's thinking. He's thinking. So what's the difference between weight and mass?
Oh,
All right, Nico, do you know?
because the weight could be different, but the mass is the same.
Right. What's an example, Emma, when a weight could be different, but the mass is the same? Do you know? She's thinking. It feels like a Monday.
No,
Tricky. Do you know Carlos? Yes. Okay, so if I'm lucky enough one day to fly to space and I get to pop out of my little straps and float around inside of whatever space vehicle is the next one that we all get to watch. If I get to do that, my mass hasn't changed. There's still the same amount of me. I'm still the same amount of stuff. My weight's different because the effect of gravity is different because I'm further from the biggest thing nearby that's pulling, which would be Earth, right? So the reason we say weight is because your mass doesn't really have force. It's just mass, right? It's just how much of something there is. The weight is gravity's effect on mass, right? So it's the gravity combined with the mass that's pushing down on the table. Yeah.
there's this good book where it like shows different how heavy you would be on
Oh,
different.
yeah, on different planets. We've done that too in Earth science. It's fun. Yeah.
Yeah, so like, I have a website on that, but like
Mhm.
it shows like on every planet.
Yeah.
Some planets that are even.
Some of them you're like, oh, I'd like to live there. I'd be really light. So,
Yeah, but then you'd be.
so in this case, so that's the action. Her weight is acting downward. All right. And then the reaction would be the table acting on what? What's the table acting on, Eunice? On Beatrix's weight in particular. This is Beatrix, right? So the table's acting upwards. If that table weren't made of wood, if it were made of paper, you would have unbalanced forces. There would be the force of gravity would be stronger than the force of that table trying to push up. So you don't think about it at the time, but like if you stand on the floor is pushing against you. You're pushing on the floor, but the floor is pushing on you. All right, so how do they cancel out? So if action is she bouncing, woo! So if action and reaction forces act on different objects, they don't cancel out. So action, the weight of Ophelia is acting on what? This is Ophelia. What's she bouncing on? A trampoline, right? Okay. So the weight of Ophelia is acting on the trampoline in a downward direction. And then the reaction would be the trampoline acting on what? Ophelia in this case. Yes, that's Ophelia. So
The name. Oh, it does.
it does have it. Yep. So the trampoline acts on Ophelia in an upward direction. Now, in this case, it's a little different than the table, right? Because this is a different material. And this material is elastic. And so it will store more energy. It will store more energy instead of dissipating it. So it'll store that energy and then release it and shoot her back up, right? Y'all like trampolines? Fun stuff, right? All right, now, this is Bartholomew. All right, if equal and opposite forces act on the same object, they result in a net force of what? What do we think? What do you think, Nico? Zero? That's right. All right, so here's an example. So Bartholomew is pushing on the what?
Wall.
He's pushing on the wall, and the wall is pushing back against who?
Yeah.
Yep, Bartholomew. All right. Bartholomew's hand. Great. But the net force on the poster that's between Bartholomew's hand and the wall is going to be what?
Zero.
It's going to be, yeah, it's going to be zero because it's not moving, right? So if I take this little ripped up piece of paper, I don't even know why I have this, and if I push on the wall and the wall pushes on me, right now this wall is pushing back harder than I'm pushing, right? Its mass is greater than my mass. I can't push it over even if I try, right? If I put this here and I don't push hard enough against it, it's going to slide. But if I push it hard enough, then, and the wall's pushing back all the time, right? So you find a point in there where you're pushing just hard enough that it becomes equal and then it's zero because they're going to cancel out. The wall's pushing this way, I'm pushing this way, and the paper's caught in the middle. So this is what it means, like, this one's not action reaction because the forces are acting on the same body. The wall is acting on the paper, my hand is acting on the paper, right? All right. So that's gonna be 0. All right, now, momentum. What's momentum? Okay, momentum is the product of an object's what and what? Okay, Eunice, what is it? It's mass and velocity. Remember these little triangles and how to use them? So if you want to find an object's velocity, and you cover up the velocity, and then what do you do?
Mass,
What do you do, Nico?
you multiply.
Well, if I want to find velocity, I'll cover up velocity. And then I do what? Divide, right? Divide mass into momentum, right? Or momentum by mass, right? Same thing if I want to find mass. I would cover it up, and then I would take the momentum and I divide it by the velocity. And if I want to find the momentum, I multiply mass times velocity. So it says here, momentum is the product of an object's what?
Mass.
There you go, mass and velocity. A product is when you multiply, right? When you add, it's a sum. When you subtract, it's a difference. When you multiply, it's a product. All right, so an object has a large momentum if the product of its mass and velocity is large. So let's considering mass and velocity here. Let's look at this for a second. All right, let's just talk about mass for a second. Do you know what these are? Do you know what this is called? Newton's cradle. All right, good old Newton. All right, smart dude. I'm gonna move the coins for just a minute so we can all see clearly, and it's nice and level because that's not level. Okay, now we want to keep some momentum going. That's going to be this moving along, the velocity moving along. So if I take one ball and bring it back, what's our hypothesis? What's going to happen? Nico, what do you think?
The ball will go. The energy will transfer to the last ball, and then that ball will go up.
Okay, so one ball is going to move on the other side, and then what'll happen? It's going to come back and do what? Push this one. Y'all have seen this before, right? Okay, there we go. That's what I'm going to do. So hold on a sec. So watch it going through. Tick, tick, tick. All right, and now it's kind of losing momentum. The mass hasn't changed, has it? But it's slowing down too, so the velocity's changed a bit. So our mass didn't change in this case, but why is it slowing down? What's causing it, Emma?
Because it's using energy when it hits the ball.
If I did this, what kind of energy is being released? Do you know? There's an energy that's being released right into the atmosphere. It's kinetic when it's moving. So right now into the atmosphere, there's friction when these balls hit, right? And friction produces what?
Heat.
Yeah. So right now there's actually heat being released as heat energy into our atmosphere, into our environment here, but it's so small that we don't perceive it. If you had like a really, really, really good super granular thermometer and you could put it in a closed system where nothing else is going to impact it, you could detect a difference. So if one caused one, then two will cause what? Two. What do you know? All right. Click, click, click. All right. So that's a good question.
Do 4. Watch it.
Watch 3. This is interesting. 3, 2, 3, 2. See it swapping? Kind of captivating, right? I could watch that all day.
It's like handing it off.
So doing 4 is kind of like doing 1, right? But now what's going to happen if I do this?
It's going to keep going. It's going to go back. No, it's going to go like that, and then it'll get transferred.
We have an action and a reaction, right?
It'll go back.
Mm-hmm.
What happened if we did 1 on one side and 2 on the other?
Well, that was just like when so 1 on one side and 2 on the other. Good question. All right, what do you think is going to happen if I do 2 here?
I think the 2 on the other side will swap on the.
You think it's going to swap 2, 1, 2, 1?
Yeah.
What do you know? 2, 1.
The 2 is a little less.
Yeah, it got a little off. Hang on, that's because it didn't hit perfectly square. There you go. That's pretty cool, right? It is. Now, what if we did just these 2 back and forth? I'm sorry, Lewis and Darcy, I know you can't see it, but you can play with it when you get back. I can't put it where you can see it. Right?
What if you did 1 and 3?
1 and 3. Okay. What do we predict?
2 and 3, because then all of them would be.
Oh, 2 and 3. Good question. What's gonna happen? 2 and 3.
It's just gonna scramble.
2 and 3. See it? Switching back and forth.
So
And that's because the mass of these balls is all the same. Now, when we get into wave theory later on this year, we're gonna build a pendulum wave, and I'm super psyched about it. But we're gonna build a pendulum wave because there are certain wave patterns that will repeat. And they'll kind of interact with one another, and it's gonna be cool. It's gonna be a big model pendulum wave, and it's very fun. All right, so let's see here. So what is the word we use for maintaining value, which means something doesn't increase or decrease? We're talking about science. Go, Nika. Yeah, you got conservation. That's the word you're looking for, right? All right, so we also use conservation. We talk about maintaining value of, I don't know. We say things like, we need to conserve our natural resources. We need to not decrease the number of trees we have. Okay, same thing. So this is important. What do you call a system where objects or forces cannot enter or leave? Do you know what word we use there, Emma? Do you know?
I want to say around system.
That's a good guess. So it's a closed system. So a closed system is you can replicate a closed system, but in some ways it's kind of an ideal situation. Okay, so what do I mean by that? So
You want it to happen?
in a closed system, we could measure that release of energy, that friction, as heat, right? But we couldn't leave it in this room and do that because there's all kinds of things going on in here. There's ventilation that kicks on, there's people moving, right? A closed system would be like in a vacuum. You can think of it like that. There's no energy coming out, there's no energy going in, all the energy is staying in the system. So in a lot of cases where there's motion involved, that system would gain heat. Hold on one second. I have a friend calling me and she knows I'm working, so let me make sure it's not an emergency. What's up? You okay? Okay, hang on a second. I'm right in the middle of class, just so you know. I'm just picking up because you don't usually call me on Tuesday. So tell me what, real quick. Yeah. Okay, if you get stuck, call mom because I've got kids. Okay, all right, good luck. Be careful. Okay, bye. My friend's brakes are dead and she has to pump her brakes and she's driving to a mechanic near me pumping her brakes. She's like, if I get stuck, or I'm like, oh my God, call my mother. She's downstairs. So anyway, there you go. So objects and forces don't leave or enter. That's what we call a closed system. All right, so conservation of momentum. So if no net force acts on a system, then the total momentum of the system does not what? Yeah, it's zero. You're right. It doesn't change. You're right. Okay. In a closed system, if the loss of momentum of one object equals the gain of momentum in another object, then the momentum is what? What will we say? One object loses it, another object gains it. What do you think, Eunice? So think about this right here. This object right here has momentum. It's going to lose momentum, but this one gains it, gains it, gains it, lose it. What do you think?
Transferring.
It is transferring it, but if what do you think?
Is losing.
So what we're looking for is it's conserved. So if this were a closed system, okay, if this were a totally closed system and there was nothing going on in this room and this was in a vacuum, then the energy from this one is going to transfer through all these, right? So it's going to lose the energy, and then this one's going to gain it, and then this one's going to lose the energy, and then this one's going to gain it. And yeah, and in a closed system, they wouldn't stop. They would just go on forever and ever, right? If you could make it work. And if they didn't go on, I mean, even if they wouldn't go on forever and ever, but you'd be able to measure the friction, the heat from the friction. But we can't do that. Like, not here. You'd have to be in like a really super special lab for that kind of thing. All right, so this is a very cool video. If you like football, even if you don't like it, it's still interesting. Come on, load up. There you go.
I like college football.
I do too.
I don't care about NFL. I like
Samesies. All right, ready.
last week.
Be Cool.
But I was camping and I did not have.
Yeah.
Bring a running back or a safety, providing with a wide receiver.
Sorry, it's blurry. It should fix
NFL
itself.
defenders have a single-minded goal to stop the ball carrier.
The object of making a tackle is you want to get the guy down and limit the amount of yards he's able to gain, especially after contact.
When a tackle is performed correctly, it's not just a thing of defensive beauty. It's also an elegant depiction of Newton's third law of motion, sometimes called the action-reaction law.
Newton's third law says that each action or force has an equal and opposite reaction. So if I were to push it against the body, that body is going to push back against me with an equal and opposite force.
An important part of Newton's third law is the concept of momentum, which in football is the mass of a player multiplied by his velocity, represented by the formula P equals MV. NFL players may not know the formula, but they're keenly aware of the role momentum plays in tackling.
It's very important when they have some speed and momentum as you're going in to make that tackle. The better to be able to do that here at age. You're.
Hold up.
Get a guy.
Pause it for a second. Let it catch up. Hold on. All right.
Away.
In every collision on the football field, Newton's third law dictates that the total momentum between players must be the same before the collision as it is after the collision. This relationship is referred to as conservation of momentum.
The law of conservation momentum says that the P, momentum before the collision, is equal to P, the momentum after the collision.
This law, represented by the formula P before equals P after, can be illustrated with a simple toy called a Newton's cradle.
But in this case, we have displaced an initial sphere, and when we let it go, it has some momentum. It's mass times velocity. When it impacts the next sphere, that momentum is transferred through the middle three spheres and then passed on to the final sphere. And so because it has the same mass, it will move away with the same velocity that the first sphere impacted the middle
Oh.
three spheres.
So
The
up.
interaction of balls in a
Hello.
Newton's cradle can
That-
help illustrate what's
What? I'm wondering if they're out there working on the road, right? Maybe they're interrupting the fiber and we're getting problems with the
I don't think
internet. That could be it.
your internet does not.
Well, they've been doing so much work out there that there's just no telling. Like,
Last week I was so confused. I thought it was my computer glitching, not the videos. And I was
Yeah.
so confused.
yeah. All right, let's try this again. Still no luck. All right, come on, do your thing. It says I have internet. That's a good thing.
Why is it called
Connect. Here you go.
Why is it called Jason's TV?
Because it's his.
Because it's supposed to be.
Because I don't much care about what kind of TV we have. I like his choices, so I say cool, but I don't. That's his thing. He decides anything electronic in this house. All right, so let's see if we can pick up where we left off. Somewhere around
No, more past that.
here.
It says that the P,
No, yeah.
momentum,
a
There we
Newton's
go.
cradle.
but in this case, we have
Saw this.
displaced an initial
Alright.
three spheres.
The interaction of balls in a Newton's cradle can
That's where we
help
were.
illustrate what's
And
known
it's clear now.
as elastic collision.
Internet, probably better.
Defined as one in which there is no loss of kinetic energy in the form of heat, sound waves, or deformation of the object. On the football field, collisions are typically inelastic collisions because kinetic energy is released mostly in the form of compression between the players' bodies and sound waves.
Inelastic collisions are the rule of the day. We see them all the time in football. That is the energy of motion of two runners. As they collide, that energy is dissipated and deforming their bodies. That's like a spring. So some of your energy of motion limits that compression. We might have heard a loud snap from our pads. Some of the energy of our collision was transferred to energy in the air to here.
While big hits look and sound spectacular, what's most important in tackling is stopping the ball carrier's forward progress.
If your pads are underneath his and you're hitting on an upward slope, you direct the energy up and you take them back. At the point of contact, hopefully that's where the ball stops play in.
Whether a tackle is successful or not, we can be certain that the same force is exerted on both players, and the total momentum before and after the collision is the same. For that, we have Newton's third law to thank.
Well, there we go. You can get some real life examples. All right, so your summary of Newton's laws. You've got your three laws. Newton's first law is the law of inertia. This is the one, how do we say that one? What are the words for that one?
Oh.
What do you think? What's the easy way to say it? It starts with objects in motion.
Yeah.
What is it? How's it go? Objects in motion tend.
Yeah, oh yeah, object in motion tend to stay in motion, object at rest.
Yes, unless acted on by an outside force, right? Okay. The second law is the one that is hard to make an easy little phrase out of, right? How do you summarize the second?
The net force of an object is equal to the product of the force equals mass times.
Yeah, F equals ma. If you can remember F over ma or F equals ma, that's the easiest way to remember Newton's second law, right? To just say, the force is a product of mass times acceleration, right? And that force is proportional to mass and force is proportional to acceleration. So if you can remember F equals ma, you got Newton's second law. All right, Newton's third law. This is how do we summarize that one? What's the quick way? It's the one we did today. Eunice?
When an object
Mhm.
exerts a force on the second object,
Mhm.
the second object will exert a force that is equal or
Yep. So every action has a
equal
equal opposite reaction. Did you see that little Hamilton nod in there? Anybody heard Hamilton, the musical? See the little people there where it says every action has its equal opposite reaction in your binder?
Oh.
Yeah, that's a Hamilton. That was a nod to Hamilton. That's a Jefferson talking to Madison. That's one of the lines from that. Yep, every action has its equal opposite reaction. All right, we're gonna skip this one for now and come back to it because I want to give you a chance to do problems. And I don't know how long it'll take you. So I'm gonna give you guys some paper and we're gonna just try a couple of problems and see how we do. Now, my rule for when you're doing problems is I give everybody like a minute or two to answer, but don't put your hand up because some people, if you put your hand up because you're ready first, you got done faster, somebody who might need longer could get real anxious. Here you go. Carlos, so we just wait and then I ask for a volunteer. I'm not gonna just call on you. All right. So I'm gonna put up our first problem. Let's see how we do. So first, problem solving strategies. So if you're applying Newton's laws of motion to a problem, and these are usually word problems in science because that's kind of the purpose of the math, right? So the first thing you want to do is identify the physical principles involved by listing the givens and the quantities to be calculated. So that means if you know F and you know M, but you need A, you write F equals and write the value, M equals and you write the value, and then A equals, and you can put a question mark or an X or just leave it as A because you don't know, right? Then you're gonna sketch it. Sometimes sketching it helps. You just draw it out. Maybe that helps. Sometimes you don't need that. Sometimes you do. And determine the system of interest. This means, am I looking for acceleration? Am I looking for force? What am I interested in? Okay. And when you draw that out in a diagram and you kind of note what you're looking for, that's called a free body diagram. And then you apply Newton's second law to solve the problem. If you're doing that, then you have to apply appropriate kinematic equations. This is for letting you know this is here because you have to assume motion along a straight line because we're not going to do anything more advanced than that because there is math to go through like motion along a curve, motion, there's all kinds of ways, right? And it can get really complex. So we're just always going to assume it's a straight line. And then check the solution. How do you check a solution to math to make sure it makes sense? What do you do? How do you do it? Like if I said 4 divided by 2, well, 8 divided by 2 equals 5. How do I know if 5 is right? What do I do to check it?
You do 5 times 2.
Yeah, you multiply back, right? You plug it in, right? Plug your answer in and see if it makes sense. All right, so here's your first one. A rider and his bicycle have a total mass of 50 kilograms. Assume that the net force acting on the rider and the bicycle is 25 newtons. What's his acceleration? This is going to be your tricky one. Do you remember what acceleration, how you find acceleration? So,
Divided by.
yeah, it's right here. This one's here so you can see it. So if you want to find the acceleration, it's force over mass. So this is here as an example, right? And then you would divide your force by your mass. And then you have 0.5 newtons over kilograms. Okay, now here's where it gets tricky. Let me show you. So, whoops, newtons over kilograms. What's a newton measured in? What is it?
And newtons measured in kilograms, kilograms
Yep.
over meters.
Yeah, kilograms over, yeah. It's how much force is needed to move a 1 kilogram object 1 meter, right? So in that case, what you end up with is you end up with kilogram over kilogram and you cancel it out. And you end up with is acceleration. So it's meters per second squared. All right, so let's try this one. All right, this one's easier. That one was acceleration. And I'm not going to give you guys, I don't think there are any acceleration questions on your test, but there are some for speed and there are some for things like this one. So a car is traveling down the highway. The driver has set the cruise control to maintain a constant speed. If the engine creates a force of 70,000 newtons, how much opposing force is exerted by the car? This one shouldn't require too much actual calculation if you think about it. This is a Newton's third law question. Newton's third law is what? Every action?
As its opposite and equal.
Right, equal and opposite. So if an engine is creating 70,000 newtons, how much opposing force? Say it. 70,000 newtons. Yes, you'd have to have 70,000 newtons because that's going to be your equal. We already know it's opposite because it says, see this word? Opposing. You got to look for those words in math. You got to look for words like product or difference. Well, in this case, opposing. So 70,000 newtons is acting on your car. So that's going to be how much is opposing. And if you were to work it out, like all the mathy math, it would look something like that. But really all you need to know in this case, because we're imagining a closed system in a straight line, like ideally, we're not going to go kooky crazy. All right. So how about this one? This one you can work. If there is a block with a mass of 2 kilograms and a force of 20 newtons is acting on it in the positive x direction. So you can insert for positive x direction, you could say left, okay, or right, or east, or west, whatever's easiest for you, just in your head. And a force of 30 newtons in the negative x direction, then what would be its acceleration? Okay, it's a little tricky. So to find acceleration, yeah, so what's the formula for acceleration?
Acceleration is F divided by
What is it?
F
Force divided by mass?
divided
Almost there, almost there. Let me see, does anybody think they can solve this one? This one's tricky. So here's what you got to do first. All right, first you have to calculate your net force. All right, so we said it was being pushed in the positive direction 20 newtons and then a negative direction 30 newtons. So negative 10 newtons is acting on it and its mass is 2 kilograms. Right, so acceleration is force over mass. F equals ma, right? So A, if you want A, you have to have F over m. So here's your F and here's your m, and it's accelerating at negative 5 meters per second squared. So if it says it's accelerating negative 5 meters, what the heck does that mean? It doesn't mean it's like, what it means basically is it's moving the direction opposite what you started.
I use a lot of when I'm doing my 3D printing,
Mm-hmm.
you have negative numbers.
Okay. Yeah.
Which is basically like there's a 0 point.
Yep. Yep.
And you can either go left
Mm-hmm.
be positive or then right.
Right. To be negative. Right. That's exactly what this means. So there you go. That's a real world
I
example.
use that literally all the time.
Very good. Okay.
Do a lot.
So I'm gonna warn you. Do you remember when we did We Love the Atmosphere? Remember that song? Okay. You don't remember We Love the Atmosphere, keeps us safe and warm down here? No, the stratosphere, all those ones. Okay. This one, yeah, that's a fun one. It's catchy. This one's fun too, but I'm gonna be the first to tell you it's cringy, and I want you to imagine that you're in some public school, or I don't know if public or private what this is, and the science teachers in your school make this video and then are like, look at us, and have you see it. Just be thankful I don't star in this video. It is cringy, but it's great as far as helping you remember. Okay.
There's a Beethoven song that we listened to in music class.
Hang on, it's not.
That reminds me of this.
Oh, yeah. So Mr. M and Mr. Parker. Mr. M probably has a crazy long last name, so he's Mr. M and not Mr. whatever. It's my sister-in-law. She has a long last name and they abbreviate it in school where she teaches. Mm-hmm. Got a bunch of them.
Things go down while us round and round. Why don't we go away? Is it because of gravity? It's other we can be alone. Yet there are things we don't know. But there's these bones, nothing new. Say, I feel rest more main rest, let's not get on a fly force, and I think the rest more main rest, let's not get on. I think the motion remain in motion, same speed, same direction, and I think the motion remain in motion, same speed, same direction, and I think the rest will remain in rest, and let's act it on by force, and I think the rest will remain in rest, and let's act it on by force. And I think the motion remain in motion, same speed, same direction, and I think the motion remain in motion, same speed, same direction. Oh no, brother, nothing bad when it's not the inertia hits. May not change is what that means, which is why you don't stop still. Now you know, so be careful. The first law of motion, but if an object is applied at force, it will continue on that course, course. Apply that difference force. What do you say? Makes it produce when a force of applying full of mass is always when force of applying full of mass it produces when force of applying full of mass is always when force of applying full of mass unless acted on applied force. And I think it was remain at rest unless acted on applied force. And constant motion remain in motion, same speed, same direction. I mean,
You been it.
same direction.
It's awesome now. I love that one. Oh yeah, that's uber cringy, but it's fun. It's fun cringy. There you go. That is Newton's laws for you.
Yeah,
Do I have it? What now?
at the trying that you type it and it comes up. There's the YouTube.
Oh, yeah.
Map.
Did y'all watch that one? What was that one? Was that the gravity one?
There's one about the Falcon Heavy
Oh yeah, the Falcon Heavy. Yeah, yeah.
conservation of Monday
Uh-huh.
conservation.
Yeah, those are all good ones that you can watch. Let me call everybody in. All right, bye Lewis, bye Darcy, wherever y'all are. We'll see you later.
Are you Zoom meeting?
They're not here at the moment, but they'll see it later.